Today's lesson is on medians and altitudes. Take a minute to read over the learning goal and scale. Find where you are on the scale before we begin the lesson. A median of a triangle is a segment whose endpoints are the vertex and the midpoint of the opposite side. A triangle's three medians are always concurrent. The concurrency of medians theorem says that the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So, the length of segment DC is 2/3 of the length of segment DJ. The length of segment EC is 2/3 of the length of segment EG, and the length of segment FC is 2/3 of the length of segment FH. If the 2/3 part is a little bit scary, look at it this way. Since the length of segment EC is 2/3 of the length of segment EG, that means the length of segment CG is 1/3. So if this is 1/3 and this is 2/3, it takes two of these to make one of these. It takes three of these to make one of these. In a triangle, the point of concurrency of the medians is called the centroid of the triangle. This point is also called the center of gravity of a triangle because it is the point where a triangular shape will balance. For any triangle, the centroid is always inside the triangle. In example 1, we will find the length of a median. In the diagram, the length of segment XA is 8. What is the length of segment XB? Since the length of segment XA is 2/3 of the length of segment XB, and the length of segment AB is 1/3, if the length of segment XA is 8, the length of segment AB is 4, or half of 8. So the length of segment XB equals 8 plus 4, or 12. Pause the video and do you try number 1. In the diagram, the length of segment ZA is 9. What is the length of segment ZC? Well, we know that the length of segment ZA is 2/3 of the length of segment ZC. So the length of AC is half of 9. Since the length of segment ZC is the length of segment ZA plus the length of segment AC, then we know that the length of segment ZC is 9 plus 4.5, or 13.5. Part B wants to know what is the ratio of the length of segment ZA to the length of segment AC. Since the length of segment ZA is 2/3 of the whole median, and the length of segment AC is 1/3 of the whole median, then the ratio of the length of segment ZA to AC is 2:1. The altitude of a triangle is the perpendicular segment from the vertex of a triangle to the line containing the opposite side. The altitude of a triangle can be inside or outside the triangle, or it can be the side of the triangle. In example 2, we will identify medians and altitudes. In part A, for triangle PQS, is segment PR a median, an altitude, or neither? Well, since segment PR starts at the vertex P and is perpendicular to side QS, it is an altitude. In part B, for triangle PQS, is segment QT a median, an altitude, or neither? Explain. Well, since segment QT starts at vertex Q and ends at the midpoint of segment PS, it is a median. We know that point T is the midpoint of segment PS because of our congruence marks. Pause the video and do you try number 2. For triangle ABC, is each segment a median, an altitude, or neither? Explain. For part A, let's look at segment AD. Well, I can see that segment AD starts at the vertex of triangle ABC and goes to point D, which is the midpoint of segment CB. So segment AD is a median. For part B, we want to look at segment EG. Since point E is the midpoint of segment AC and point G we don't know, This could be a mid-segment, but we're not sure. So it's neither an altitude nor a median, so we're going to write neither. For part C, let's take a look at segment CF. Since segment CF starts at the vertex C and is perpendicular to side AB, it will be an altitude. The concurrency of altitudes theorem states that the lines that contain the altitudes of a triangle are concurrent. In a triangle, the point of concurrency of the altitudes is called the orthocenter of a triangle. The orthocenter of a triangle can be inside the triangle like it is on the acute triangle. It can be on the triangle like it is here on the right triangle, this point here, or it can be outside the triangle like it is here on the obtuse triangle. In example 3, we will find the orthocenter. Triangle ABC has vertices at A, 1, 3, B, 2, 7, and C, 6, 3. What are the coordinates of the orthocenter of triangle ABC? Let's start by plotting points A, B, and C. Now that we have triangle ABC, let's find the altitudes of our triangle. We need at least 2 in order to find the orthocenter. Since side AC is a horizontal line, we know that the line perpendicular to it will be vertical. So if we start from vertex B and go straight down, we will have our first altitude. Now we need to find a segment that is perpendicular to either side AB or side BC. Since I can see that the slope of side BC is -1, I go down 1 to the right 1, down 1 to the right 1. I know that I want my slope to be perpendicular, so it would have to be +1. Since we want our altitude to start at vertex A and be perpendicular to side BC, we want our line to contain point A at 1, 3 and have a slope of 1. Since we know a point and the slope of our new segment, let's write an equation of this line in point-slope form. Now let's rewrite our point-slope form to slope-intercept form so that it's easier for us to graph. Now we have our y-intercept of our line at 2, and we know that our slope is 1. So we can plot the line that passes through 2 on the y-axis and has a slope of 1, up 1 over 1, up 1 over 1, up 1 over 1. Our orthocenter would be the point here at 2, 4, where our 2 altitudes intersect. Pause the video and do U-try number 3. Triangle DEF has vertices at D, 1, 2, E, 1, 6, and F, 4, 2. What are the coordinates of the orthocenter of triangle DEF? Let's start by plotting the 3 points and making our triangle. Since segment DE is horizontal, we know that the line perpendicular to it will be a vertical line. Since the angle opposite side DE is F, it will be the vertical line from point F down to side DE. So our first altitude will actually be side FD. Since side FD is a vertical line, we know that the line perpendicular to that would be a horizontal line. Since the angle opposite side FD is angle E, we would start at E and make the horizontal line to segment FD. This altitude would be side ED. Since all 3 altitudes are going to be concurrent, we don't really need the side that is perpendicular to side FE. So where side FD and ED intersect here at point D, this will be the orthocenter of triangle DEF. Here is a quick review of the special segments and lines in triangles and their points of concurrencies. Remember, the perpendicular bisectors are the segments that are perpendicular and bisect each side of the triangle. Their point of concurrency is called the circumcenter. The angle bisectors of a triangle are the segment that bisect each angle of the triangle. Their point of concurrency is called the incenter. The medians of a triangle start at a vertex and have an endpoint, the other endpoint, at the midpoint of the side opposite the angle you started from. The point of concurrency of the medians is called the centroid. And finally, your altitudes start at a vertex and are perpendicular to the side opposite that vertex. The point of concurrency of the altitudes is called the orthocenter. Now is your chance to see how well you understand the lesson. Pause the video and do the lesson check. Don't forget to check your answers on the next slide. If there's a question you don't understand, please be sure to ask me in class. Now that you have the hang of the lesson, go ahead and try the challenge. Take a minute to reread the learning goal and scale. See if you've climbed any higher on the scale since we've completed the lesson.